Okay, so oxidation reduction. And this process is really important. There's a lot of the cool chemical reactions that end up being oxidation reduction. And what it means, which we'll learn in the next slide, but basically these are two processes that happen in the same reaction. So in a complete chemical reaction, it's not just oxidation or just reduction. It's both happening at the same time. One thing in the reaction is being oxidized, one thing in the reaction is being reduced, whether it be an element, a compound, or whatever. They can be reduced or oxidized. Maybe you've heard of the term oxidation before. It's a very common term. It happens a lot. Like if you have the oxidation of a metal, right? Let's say it's iron. That's rusting. That's what rusting is. We'll learn more about that process later, but it's an oxidation. So oxidation, you can imagine by the name, it involves what element? Oxygen, right? So it actually involves this oxidation reduction. You're going to be talking a lot about hydrogen and oxygen. So wherever you don't have hydrogen or oxygen, chances are you're not going to have an oxidation reduction reaction, but you still might. But most of the time, it does involve oxygen or hydrogen. So here's what they mean. So when you have something that's oxidation, right? When oxidation occurs or when something is oxidized, that's another term for it. That means it either gains oxygen, right? Oh, no duh, right? Oxidation, gaining oxygen. So you're oxidating something, meaning putting in oxygen to it. Or it can mean you're losing hydrogen. So hydrogen and oxygen are antagonists in this case. They're opposites. So if you have oxidation, you're either gaining oxygen or losing hydrogen. So these four things we're going to go over, but not every one has to happen at the same time for it to be oxidation. If you see one of these things, that means it's oxidation. So gaining oxygen, losing hydrogen, also losing electrons. Now, sometimes you might have elements that just lose electrons. So for example, my pen out, let's see. So if you have a very simple reaction that's, let's say, silver metal, and then silver metal ends up losing electrons to become silver 1 plus 1 electron, this is oxidation because it loses electrons. So here, this electron, this 1e minus, was in the silver. Now it's not. Now when the electron leaves the silver has a charge of +1 after it leaves. So that's an example of an oxidation, even though no hydrogen and no oxygen is involved. It's still losing electrons. And what this does is, in turn, increases what we call this thing called the oxidation number. Now, we're not going to get too in-depth about oxidation number. There is ways to figure it out for every element in a chemical reaction. But basically, it directly corresponds to the amount of electrons lost or gained. So these are very similar to each other. So the oxidation number, in this case, for the reactant, this silver that doesn't have a charge, would be 0. And the oxidation state for this number, for this Ag, would be +1. So an oxidation means increase in oxidation number. You have 0 to +1. So that's an example of that. Now, a good question would be, oh, how do you determine oxidation number? So again, could get very complicated, but we're going to cover that for very simple, what we call half reactions, which are these, where you just have directly the losing or gaining of electrons. But it could get really in depth. Like this is a pretty complicated redox. We call it redox. It's another term for it. Because rather than saying oxidation reduction all the time, we say redox. This is a very complicated redox reaction where, like, the nitrogen in this case is a -3. Over here, it's 0. So then it gets oxidized. But how do I figure that out? It's difficult. There's a lot of math that's involved with that. But we're not going to talk about that in this class. Okay. Any questions on that? Okay. Then you have the flip side, which is reduction. So reduction is the exact opposite of oxidation. So if one occurs, the other one has to occur. Because if you have oxidation, something's losing electrons, where do the electrons go? They have to go somewhere. They have to go somewhere to another compound, to another element, whatever the case may be. So they have to transfer the electrons to something that's being reduced or having reduction to gain those electrons. And similarly, if oxidation gains oxygen, where is it getting the oxygen from? Oh, it's getting the oxygen from something that loses the electron or the oxygens. And then with reduction, when you gain hydrogens, you're getting the hydrogens from somewhere that lost the hydrogens. So if that makes sense. And then increase in oxidation, the oxidation number directly corresponds to electrons, like I said before. So if you gain electron, or sorry, if you lose electrons, your oxidation number increases because you're losing electrons, meaning you're losing negatives. Electrons are negative. So if you lose negatives, you get more positive. But the electrons have to go somewhere. They go to the reduction side of the equation. That means a gain of electrons and a decrease in the oxidation number. So these two things go hand in hand. And here's exactly what they mean also. So this is a very good acronym that's helpful in a lot of textbooks called oil rig. So definitely remember that. So oil rig means oxidation is losing, is loss, right? And loss of what? Loss of electrons. Loss of electrons. Reduction is gain. Reduction is gain or gaining of what? Of electrons. It's very important. So that's a very easy way to remember oxidation reduction. Just remember oil rig. Oxidation is loss. Reduction is gain. Very simple. So here's an example of one of these reactions in full swing where we see this is combustion. So now when you burn something, that's an oxidation reduction reaction when you burn, because what's happening is you have substances that are, yes, they're changing the oxidation state, but if we don't want to look at that and we want to understand it without the numbers, we can just see the loss and the gain of oxygen or hydrogen. So if you take this CH4, right, and you follow the carbon from the left to the right side of the equation. So here's carbon on the left with CH4. Here's carbon on the right as CO2. What's happening? It's losing hydrogens and it's gaining oxygens, right? What does that mean? That means it's being oxidized, losing hydrogens, gaining oxygens, oxidized. And if I were to do the math and get the oxidation state, which you don't have to understand, the carbon would be -4 over here, and the carbon would be +4 over here. So that means the oxidation state, if we look back at our thing, we can say gain of oxygen, done. Loss of hydrogen, it's done. I did it too. And it increased oxidation number. So everything's accounted for here. And then, like I said, if you have to have, or if you have one, meaning oxidation, you have to have reduction. So what's being reduced? Look at the oxygen here. The oxygen is just O2. And what's the oxygen happening over here? The oxygen is gaining hydrogens. Now, it's not gaining hydrogens everywhere. This oxygen over here is paired with a carbon. That's completely different. But this oxygen is O2. You can say that from here to here, it's gaining hydrogens. So if that's the case, that means it's being reduced. So that means the oxygen is being reduced. So not all of those four metrics have to happen, talking about electrons, oxidation number, oxygens, and hydrogens, but at least one of them does. So I would say oil rig is good to memorize, but if I were to classify an oxidation, which I would expect maybe you should do, or you would have to do maybe on exam, is to classify if the reaction is oxidation reduction. So what you'd have to do is see, all right, is some substance gaining oxygens or losing hydrogens? If it is, then it's going to be oxidation reduction. And is the other substance doing the opposite? So keep that in mind. Any questions on that? No? Okay. Okay, so further, so here's what I'm going to do. I'm going to copy this reaction, put it here. Okay, so what you can say, and so I'm going to talk about this example more. So I'm not going to go over another different example. We're going to talk about more examples later, but you just follow this example. Okay, so another way you could think about it is there's these things. So a common term is called an oxidizing agent, right? So this oxidizing agent, what it means is it's something that causes the other thing to be oxidized. Now it's a weird way to think about it, but it's the thing that's not being oxidized, but it causes the other thing to be oxidized. So let's just reiterate this equation again. You have the carbon that has hydrogens, it loses the hydrogens and gains oxygens. That means the carbon is oxidized, right? So it itself is oxidized. That means it doesn't cause oxidation. That means it is the result of oxidation. It is what's being oxidized. So, okay, why is it being oxidized? Because of the other thing it's paired with in the reaction, which is oxygen. So oxygen is one of the best oxidizing agents, which makes sense, right? Because oxygen, what gives oxygens better than oxygen? It could just add on to something. There are a lot of other oxidizing agents, but oxygen is one of the best ones. So, hold on. My cat was just whining for no reason. Anyway, so that's what so an oxidizing agent is the thing that contributes to giving the oxygens to the other substance. So it's not the thing that's being oxidized. Now, a reducing agent is something that causes the reduction, meaning what it does is it gives the hydrogens, and instead of giving oxygens, it can either give hydrogens or help take away oxygens. So in this case, carbon, or even CH4, whatever you want to look at it, would be the reducing agent, because it itself is helping the oxygen be it's helping the oxygen act as an oxidizing agent. So it's helping the oxygen's actually being reduced. So they're opposites of each other. There's a lot of opposites to think of in this redox concept. So I'm going to go over it one more time. So CH4 is being oxidized. How do we know that? Because it is losing hydrogens, right? Going to the right side of the equation, losing hydrogens, and also it's gaining oxygens. So that means it's oxidized based on the definition. On the flip side, oxygen is gaining hydrogens. If you compare it to here, that means it's being reduced. So oxygen is being reduced. If that's the case, the agents, the way to define the agents is just the opposite. So since carbon is oxidized, carbon is the reducing agent. Since O2 is being reduced, O2 is the oxidizing agent. So they're opposites. So if I give you an exam, first part of the question, which one's being oxidized? You would look and you would see which one is gaining oxygens. That one's being oxidized. Then you would see which one's the reducing agent. Okay. If it's being oxidized, it is the reducing agent. If it's being reduced, it is the oxidizing agent. So let's do another example. Let's look at an equation for rusting. So here's rusting. So for rusting, you have, the way it occurs is you have something iron, right? And you have the elements, it's exposed to the elements. Let's say when you're little, you had your bike, it's outside, and eventually it starts to rust. Why does that happen? Because it's exposed to the two main oxidizing agents in the environment. Good. So good one. Water is one of them. And also oxygen gas is another one, but water is the main one because it actually makes the oxygen stick. So, so what would happen is you have the iron, it reacts with the water and the oxygen in the atmosphere. And it actually, since the oxygen's there, remember we said oxygen is a really good oxidizing agent. It's one of the best ones, meaning it can give its oxygens to something else, in this case, a metal. So in that case, what it would do is it would create iron hydroxide. Or it could even create iron oxide. That's one also. But in this case, this equation talks about iron hydroxide. And what that does is it creates this color. It creates this rustic color. That's iron hydroxide. So that's how it occurs. So basically strips the metal and makes it react with oxygen to oxidize it, causing it to change. This is a chemical change, causes it to change into a different substance, which is iron hydroxide. And then that iron hydroxide could react more into iron, from iron 2 hydroxide to iron 3 hydroxide. So remember we talked about when we went over naming, this would be the one in the first equation would be iron 2 hydroxide because of the transition metal naming, and the bottom one of the bottom equation would be iron 3 hydroxide. And no, there is no iron 4 hydroxide. Okay, so that's an example with rusting. So let's go back and just go over some more real world examples. So if you ever heard of photochromatic lenses, there's an oxidation reduction reaction occurring in them too. So basically what happens is it involves silver. Now there's actually pieces of silver ions in the glass. And what that does is when it's oxidized, or sorry, when it's reduced, when it's reduced, it forms a darkening because it makes it more of a, instead of it being charged, it's more of an inert. So it causes it to like block light more. But it blocks light in such a way that it doesn't get completely dark, since the silver is dispersed evenly throughout the glass. It's made in a factory in a certain way to standards that it darkens the lens. So photochromatic lenses, you have the more light you have, light can cause oxidation too, and light can cause reduction. So the more light you have, the more reduction of the silver you have, meaning the darker the lenses get, and they kind of adjust to the amount of light. So that's how this happens. So those are photochromatic lenses. It's pretty cool. And also you can have oxidation reduction is the main main way of producing electricity. So you can have, because in this equation we talked about one thing, if we go back, the loss, or really the transfer of electrons. So we talked about losing electrons, gaining electrons. So that means there has to be a transfer of electrons. A transfer of electrons is indicative of a current, and current creates electricity. So here's an example of that. If we were in the lab, we'd be doing this experiment where what we would do is we'd put in, this is a silver chloride, the liquid. The liquid is silver chloride. And the metal is copper. So what would happen is the silver ions from the silver chloride would be reduced. So they'd be reduced, and here's the equation they would be reduced by. It would be Ag plus an electron yields Ag. The electron would come from the copper metal. When they become Ag, they become solid. And they actually form as crystals like this. Like you see the metal actually form, and it will come out of the solution. This is really cool. So this is a soluble silver. There's silver in there, but it's soluble, meaning it can dissolve in the water. Once you put in copper metal, a reaction occurs, and then the metal or the silver is no longer soluble, and you can actually mine the silver. You can get the silver out of there and you can sell it. But I mean, this is a very small scale, but you can do that. And then on the other side, what's happening with copper is the copper metal originally had electrons in it, then loses those electrons to become charged. So it'll become copper plus electron minus. And what this does is, because it's positively charged, it now can be dispersed in the solution and dissolve. And it can dissolve because it's positive charge. The water has positive and negative charges, so it can dissolve the copper. And a copper solution is actually blue. So that's something that's interesting about copper is we know it as like a bronze color, or really copper color. But when it's in a solution, in a soluble water-based solution, it's actually blue. So basically what's happening here is the states are switching from solid to liquid because, or solid to aqueous, because of the loss and gain of electrons of the metals. So this is a way of producing electricity because you have electrons moving and a current is being created. So the way these, in this example, the way the copper and the silver could react as electrodes. So electrodes, and this would be easier if we were in the lab to talk to just experimentally observe. But electrodes are kind of like, well, let's write batteries. Batteries are a type, have electrodes, which can transfer electrons from one side of the battery to the other, from the negative end to the positive end. So there's two types of electrodes. There's the anode and there's the cathode. And it's very easy to determine which one's which. So we're basically attributing a bunch of different terms to the same thing. So the anode is where the oxidation occurs. Anode oxidation. And then the cathode is where the reduction occurs. So let's take this and we'll put it towards an equation. So here's what I'll do. I'll write the equation for the silver and copper. So you have silver that's in the solution plus copper that's not in the solution yields copper plus silver that's solid. I'll put solid here and solid here. Okay, so what's happening here is that let's first characterize what's being oxidized, what's being reduced. Now, there's no oxygen and there's no hydrogen. So what's another measure? How can we determine what's oxidized or reduced? Anybody?
The charges, so the electrons.
Good. Yes, the movement of electrons. So remember oil rig, oxidation is losing. So meaning electrons. Which one of these is losing electrons?
Silver.
I don't think so. Electrons are negative, right? Yeah. So losing electrons, what's going to happen to the charge? Is it going to go up or down?
Does it go down?
Up.
Up. So then which one would it be?
Copper.
Good, copper. So yeah, it's kind of difficult to understand because it's a lot of opposites. So if you're losing electrons, electrons are negative. You're losing negatives, you get positive. So oil rig, oxidation is losing electrons, meaning the number goes up or the charge goes up. Reduction is gaining. You're gaining electrons, charge goes down. So copper is being oxidized because the charge is going up because you're losing electrons. Then the silver is being reduced because the charge is going down. And that's the physical word of reduce or reduce something to me means to decrease it. So that kind of helps a little bit. Even though the definition of it means you're gaining electrons, but you're actually reducing the charge and reducing you're basically reducing the charge. And then we can attribute based on, so there's a lot we can do. Based on what we know is oxidized and reduced, that's the hardest part. The next thing we can do is say that because it's oxidized, it's the reducing agent. Remember they were opposites? Something's being oxidized, it's the reducing agent. Something's being reduced, it's the oxidizing agent. And then we can say, because it's oxidized, it's the anode, based on what we learned just now. And if it's reduced, it's the cathode. So we can say three terms for every redox reaction. First, figuring out which one's oxidized, which one's reduced. After that, we can say, because it's being oxidized, it is the reducing agent, meaning it's causing the other thing to be reduced. And then we can say, because it's oxidized, it is known as the anode, where the electrons go away from and they go towards the cathode. So electrons, they generally travel from anode to cathode. So there's a lot there, but all the terms go together very nicely together. So any questions on that? No? All right. So some more examples. You have batteries. So we have batteries where you have, you have nickel and cadmium acting as the anode and the cathode rather than silver and zinc, or sorry, silver and copper. Zinc can also be used in these reactions too. Like you have zinc batteries, you have lithium batteries, things like that, but you nickel cadmium. Fuel cells, where you combust things. So you can combust fuel. We talked about rusting already. So in the rusting equation, just to do another equation with redox, so we'll look at the first equation. So iron, in this case it's weird because iron, technically you could say, is gaining oxygens and hydrogens. So what happens? It's still going to be oxidized because oxygen has a higher charge than hydrogen does. It's -2 and hydrogen is just +1. But that's a difficult one. But what you can say is that this oxygen is gaining hydrogens, right? So that means it's being reduced. And the iron is gaining oxygens. Also, it's gaining hydrogens, but it also, the oxidation number of it does increase. So it's being oxidized. This is a rather difficult one to see which one's being oxidized or reduced based on what we know. So I'll give you a little bit simpler ones. They'll be like the silver and the copper. That's something that you should expect. But this one's a little bit more complicated, but the same rules apply. Remember, we talked about those 4 things, right? We talked about the gain for oxidation. We talked about the gaining of oxygen, the losing of hydrogen, the losing of electrons, and the increase in the oxidation number. So not all of these occur at the same time. Only 1 or 2 of them, or if only one of them really needs to occur. Now for iron, we have the gaining of oxygens, and we have the losing of electrons and gaining of oxidation state, which is not that apparent here because this is a more complicated one. But for the oxygen, it kind of is, because we could say, here's oxygen. Now the oxygen has more hydrogens next to it. So we can say it gains oxygen, or sorry, it gains hydrogen, which means it's being reduced. So it's being reduced, the iron is being oxidized. Also, another key thing is, if you have metals reacting with oxygen, almost all the time, the metal is going to be the thing that's oxidized. So wherever you have a metal, it's always going to be oxidized when it's in the presence of oxygen. So because oxygen is a very good oxidizing agent of really anything, of any metal. Okay. All right, another example is silver tarnishing. So silver tarnishing is very similar to rusting, and it results from the reaction between silver on a surface, let's say like an antique plate or something, and then with hydrogen sulfide in the air. And this leaves a black film of oxidation on the silver called silver sulfide. So an example reaction would be, this isn't the full reaction, is more byproducts, but let's just say we have Ag plus H2S yields Ag2S plus H2. Let's just say that's the equation for, and we can balance it. Done. All right. So we can say that what's happening here. So the sulfur is losing hydrogens, right? It goes from having hydrogens to losing hydrogens, right? The sulfur has no hydrogens. Therefore, that means sulfur is being oxidized, losing hydrogens, and the silver is being reduced. That's one way you can look at it. But that's not actually, so that's based on what we know. In reality, so I'm not going to give you this kind of a question either, but in reality, it's actually the opposite. The silver is being oxidized. And the reason why is because of those oxidation numbers that we didn't talk about and we're not going to get heavily into. But what happens is here you have this oxidation number of silver is 0. This oxidation number of silver is +1. So it's actually being oxidized. But based on what we know, see how I mean it gets complicated? Because based on what we just learned from the losing or gaining of hydrogens, we would say the opposite. But the oxidation numbers tell us otherwise. So we're not going to go crazy with the oxidation numbers. We'll do pretty simple equations, kind of like the one we saw with the silver and copper. So here's what tarnishing looks like. You can actually get rid of tarnishing on an old thing from undoing the reaction. So if you can polish it, and what will happen is it actually strips some of the silver. And then the alternative is allow aluminum to reduce the silver in the presence of the solution, sodium bicarbonate. So you can use sodium bicarbonate and aluminum, and you can actually strip away the oxidation and actually reduce the silver back to its original state. And then a lot of explosions, a lot of explosives are oxidation reduction, and they're really complicated equations. So here you see 152 moles of ammonium nitrate, right? So ammonium nitrate is fuel that can react with some fuel and create explosions. So yeah. Okay, so we're almost done. Now oxidation in oxygen. So oxygen is, like I said, one of the most important oxidizing agents, one of the most powerful ones too. And it can exist in the atmosphere as 2 molecules, right? We know oxygen gas is O2, and also we know ozone. Ozone's O3, and it's in the atmosphere, and it protects us against solar flares, against radiation, and it's there. So the ozone layer is actually still there, and it's actually there. So the ozone layer is all back. That's something that not many people know. Remember maybe when you were little, you've heard about the ozone layer that, oh, it's disappearing because of all the carbon emissions and all the different things that we're doing to the atmosphere. And here's just the importance of it. It serves to protect life on Earth from harmful UV radiation. Okay, so some of the UV radiation still gets in from the sun, but not the higher energy particles. But still, the ozone layer is back. There's no hole anymore. And that's something that people don't report on, but it's not there anymore. So we've actually, since 1996, after we put in, there was a bill that was passed in the US and also in most other countries to limit what we call CFCs. So CFCs, which is called chlorofluorocarbons. So what that means is you have a carbon with a fluorine and a chlorine on it. That's basically it. Or it could be multiple. Like that's a chlorofluorocarbon. They do get more complicated, but these are bad. These will actually react with O3 and make it O2 and bring it down into the air. And it'll actually deplete the ozone layer. So once we banned CFCs, the ozone layer started to magically come back. And in 2016, I think, we measured the ozone layer was 100% back. So, ta-da, we fixed it. So that's some things that we do. We're fixing the environment, and it's a lot better than it used to be. So that's good. So ozone, very important. Okay. Also, you have other oxidizing agents, hydrogen peroxide. So it's a disinfectant, also used to bleach hair. So that's another oxidizing agent. That's good. You have other ones. I'm not gonna get into too much detail, like bleach. It oxidizes fabrics. Potassium dichromate. Oxidize alcohols and turn green when reduced to chromium 3. And that's used in breathalyzers. So Hopefully none of you will have to be breathalyzed ever. You all follow the law, but that's a thing. Benzoyl peroxide, that's antiseptics. And then also, so then let's go to the flip side with reducing agents. Some things that are reducing agents you have in the production of different metals, such as tin. Tin and other metals don't occur naturally as just the metal. So if you're in a mine, right, metallurgy is really the refining of metals. That's what that means. So if you're in a mine and you're kind of trying to purify different metals, you can't just dig and find, oh, I found some tin. And tin's pretty expensive. Like tin's a really good metal to have, and it's used in production of a lot of things. But you can't just get tin. It's usually in the form of tin oxide. Now, what you can do is you need to do some kind of chemical process, some kind of oxidation reduction reaction to strip off the oxygen from tin. So if you add carbon to the tin, what will happen is the carbon will be oxidized to take the oxygen off of the tin will be reduced, and the tin is now solid tin. So you can do that. And aluminum is used to reduce chromium oxide to chromium metal. Yeah, here's another example. If you want to get chromium, you can kind of use usually these metals in the ground occur as oxides, a large majority of them, because most things on Earth are actually already oxidized because they've been on Earth for millions of years and they've been exposed to oxygen sources. So even if you have chromium in the ground, you have tin, you have aluminum, you're mining for whatever metal you can find, iron, usually it's in the form of their oxide, iron oxide, chromium oxide, tin oxide, things like that, aluminum oxide. But you can undo those processes by pairing it with a better reducing agent, allowing to reduce that metal oxide back to its original metal form for it to be used in factories. So that's probably the biggest part of redox, of where we use it, is in all of these factories for refining metals, because when you get them out of their oxide form by treating them with a reducing agent, allowing the oxygens to be stripped off of the metal so we can purify it. So that's pretty cool. Then we have antioxidants. So antioxidants are very important. I'm sure you've heard of a lot of different types of antioxidants. Vitamin C, all the different vitamins act as antioxidants for the most part. You have different foods have antioxidants, like these different shakes they have, these vitamin shakes, and things like foods like broccoli have a lot of antioxidants. But what that means is things that strip away oxygen. So an oxidant, we have antioxidant, right? So we can reduce the word to oxidant. An oxidant is something that forms a free radical oxygen in our body, or it can cause free radical oxygens to form in our body. That's not good. And what a free radical oxygen is if you have just oxygen by itself, usually oxygen is O2. If you have just oxygen by itself with a free electron. So remember we talked about electron dot structure, and in those dot structures, we had usually 2 electrons. But if you have 1 electron, that's very reactive. And these oxygen radicals are actually in our body all the time, but the idea, and they actually contribute to aging, disease, really everything bad. They contribute to everything bad. So what they would do is since they're so reactive, they can react with our DNA, and they could denature our DNA. So if we have our DNA strand, that's a nicely drawn DNA strand, it will react and it will bind to our DNA. We have oxygen, right? Then when the DNA replication occurs to try to multiply our cells by mitosis and grow our either skin cells, our organs, or just to replenish our cells, this DNA will split into 2 separate DNAs, and then it will be replicated. But once the replication gets to this free radical oxygen that's bound to the DNA, the replication reader, which is the protein, doesn't know what to do. It's like, oh, this is damage. So I'm either going to skip it or I'm going to put it in there anyway. And if it puts it in there anyway, that can lead to a mutation. Or if it skips it, that can lead to a mutation. Either way, it complicates. It's kind of like having a speed bump on the road. It could, if you have enough speed bumps, it could cause your axles to fall off or your wheels to get misaligned. And over time, you could die because you have mutations and you can get cancer. So that's very extreme. But these free radical oxygens are the #1 killer of people because they cause so many different diseases. And age, I mean, also, if you die from old age, you're technically dying from oxygen radical buildup over time because that mutates your DNA, that causes you to age, your organs begin to age, and your metabolic processes slow down. So now I made that seem terrible. I made that the oxygen radicals seem like the worst thing in the world. So your natural question should be, how do I prevent it? And the answer is not only antioxidants, but antioxidants are good or are fantastic for limiting them, and it's just healthy to have them. But to not get to behave in a way that doesn't give you oxygen radicals in the first place. What that means is not eating bad food. Bad food meaning like cookies and cake and just not good, like not healthy food. And like things that are like meat that's like with nitrates in it and like all this like steak and everything, like juicy, even though it tastes really good, like a juicy steak, but things like that with all the different chemicals and processes that are done to make those meats, you have a lot of oxygen radicals that can form in your body from ingesting those. Also, alcohol consumption causes oxygen radicals. Now, I know some of you don't like to hear that, but it's true. So if you want to limit these oxygen radicals, it would be good not to consume alcohol. So also obviously don't do drugs and things like that because that can contribute to it as well. But basically, and also exercise is good. That limits the oxygen radicals. So basically every behavior that you talked about, or that every behavior that you learned since you were little, that is good behavior, such as eating healthy, exercising, not consuming alcohol, not consuming drugs or bad food, the reason why we tell you that is because it limits the oxidation radicals that can harm your DNA, cause you to mutate, and cause cancer or other disease, heart disease, and other things like that. So there's all a purpose. There's a purpose for all this. Okay. So reducing agents, hydrogen is one of the best reducing agents, just similarly to how oxygen is one of the best oxidizing agents. So that makes sense. And it can be used for both metals and non-metals. But if you add, in this case, is tungsten oxide, and if you add hydrogen to tungsten oxide, you get the tungsten. And tungsten is very important. Tungsten is a really important metal that is, I think it's the highest boiling point, I think, of any metal. It's the most heat resistant. So that's used in a lot of different things, making different types of things. Like if you have, there's tungsten lamps, there's tungsten electrodes, there's different types of things that tungsten could be used for. Also, okay, we're not going to talk about the catalysts. Oxidation reduction also occurs in living things when you do photosynthesis, when you do cell respiration. There's a bunch of different processes that rely on the redox reaction. So photosynthesis is one of them. And yeah, it's not really biology class. We're going to go too in depth about that. But anyway, so that's about it for the lecture. Less than an hour. It's pretty good. So are there any questions?